Um, I hope this video lasts very long now. Okay. So, next is ergonomics principles. So, Namdi, why are you making this video? Diagram. You're making this video for yourself. You know your autism, ADHD, Asperger's, learning disability. You're gonna get old. Everyone gets old. But about biological sustainability of you, ergonomic housing, everything ergonomic, based on bioergonomic, biodiversity, biological, meaning biological symbiotic, genetic to phenotype model. Genes like genes are the encoding structure, the code itself, but the genes is not really the feature. The key. It reminds me of my property set. All properties like a vector can be modeled as you can have a Cartesian vector, or you can have a polar vector. But the vector is because I'm thinking of matrices and sparse geometry. But that's what I'm saying too. The vectors are, and the term sparse, like locality sparse, like made up of many things, like different models. That's a sparse. I mean, it doesn't mean like local sparse. It means like sparse means like can be made up of a lot of things, but we don't know what's actually made up of. It's based of what is this made up of. So you can think of it as a vector has to be modeled as a you can have in a plane of a polar system. You can have a move to one direction and rotate x and move y. Rotate x and move y based on sine, cosine, and tan, and then move y to one direction. And that's the basically the isomorphic layer to this model is displacement. So you can displace a vector in x, y, the Cartesian colors. We have a different metric to do it. Different way to do it because there are different systems you're using to do that thing and resolve the system with a DAG, so you can convert a polar system in real time to a DAG system. So basically, you gotta remember that. So what you're saying today is this on bioergonomics. I'm gonna try to do it manually. Let's take a vector 39 xy xyz 39 12. Now this is just a standard number system. This is called a Cartesian vector. Now I think it's saying a vector rotate y. Yes, pitch. Basically, the polar system for this three of the vectors like roll, pitch, yaw. So basically, this is like for neurodivergent people. So the Cartesian system represents like neurotypical, very boring people. But this can be neurodivergent too. That uses Cartesian first. So you can call it Cartesian one, neurodivergent Cartesian one, neurodivergent first, type A. Type A neurodivergence, just autism, and then you can cause the polar one autism ADHD model. And this was a dual modeling. So basically, I'm stating Namdi to you and to my viewers, I can have a polar system of SOHCAHTOA. Sine opposite of a hypotenuse. Sine equals opposite of hypotenuse. Sine opposite of a hypotenuse. And this is like a y rotation. So this is the pitch, roll, and the yaw. I mean the roll, pitch, yaw. So the roll is basically the sine is the cosine. So if something rolls, it's cosine x. The pitch, roll, pitch is the y. Pitch y. So basically, I'm trying to formalize it. Pitch x to pitch y sine x, and then cosine z. Yeah is cosine SOHCAHTOA. So the tan of the tangent line around the normal places can be reduced to the yeah, and that's yeah. But to get a z axis, so you don't. This is yeah. Basically, my tangent line is related to the displacement of the system in the highest dimension. Because the highest dimension is the projective vector. So you gotta remember the rules basically. Tan z, but the tan function is very important here. But you don't really you can use tan for calculation bidirectionally between the y and the x. Let me try and demonstrate that. So SOHCAHTOA tan z. So the 396. So let's try to rotate 45 degrees, and then pitch the roll 45 degrees. Okay, roll 80 degrees, 86 degrees, something non-uniform, and then pitch roll pitch roll pitch move then 10 degree, 10 25, 26 centimeters, 26 meters. Let's say 10 meters, 10 meters, 10 meters. That's 10 steps, really. 10 meter, 10 feet, 10 feet, a foot, 10 feet equals 1 feet. 10 feet, let's call it. So you got like 86 rotation, one direction, 10 feet walk, 10 feet walk, and then the watch, roll, pitch, yaw, and then the levitation, like the hover, this one is very important for you to understand that your brain is different based on interpretation. So your goal here is to try to formalize this formalize this properly as a standard problem. So you can try to 86 degrees I rotate to my body, 10 feet I walk 10 feet, and then I do jump in the air like 5 meters. How can I jump? 2.5 meters. I'm 6'4", 6'4", so I can try to drop 3 feet 4, and then on top of an obstacle. 6 feet 4, 6 feet, 3 feet. So walk for jumped 3 feet high. So I'm saying to you, there's an isomorphic layer which are called property sets. The property set model is very important to understand. So if I take this Cartesian 396, there's a uniform one. There's the same one. There's something. So why this project is important to you? This is an introduction. No bureaucracy. The problem is saying the model of Cartesian system, two-polar system, is isomorphic, but it's not because we don't. Basically, you think of it like a working theory. You don't have the like a hypothesis. You can hypothesize that I prefer the maths I'm framing. My frame of reference isn't because of the Cartesian. I don't like Cartesian. I can't work with Cartesian. I may only work with polar systems. The polar system is uniform to me. It's more easy to work with, or whatever it is, whatever has based on my high or soul problems, my neurodivergent capabilities. Therefore, if the polar system is much easier for me, transferring to the Cartesian seems like a second thought. It's like it's not about being normal. It's about having the right system that work for me. So what I have to do for directed biological evolution of computers is develop a bidirectional system that doesn't lock users based on forthright and fail-safe models. For example, the Cartesian system and the polar systems delegate tasks. So you have to replace this to your viewers. So this is just a scribble, my scribbles here. So I'm writing something down. So I can try to formalize this properly. So the goal is to define the field. The field is like wherever the plane, wherever the operation happens. So it's not about the complex number field, everything. It's about having a set space, a geometric space that aligns with our problem, wherever the property set is. Now, a property set is a set of properties that the model uses. Like, it can be functions or anything. That anything that's being consumed is a property. Anything that's being used is a property. It can be enumerated. It's not hidden. It's not private. It's property. It's used. It's like a global. Anyone can access it. It's just a main characteristic. It's a property. And a property set is things that allow that properties to interact. Like, the functions, the things that define that property, the full outcome of the property. Maybe it's a subset of the information, the informatics, that's not basically you have like not enough information, which could you can have like 25% based on PLP framework informatics, and that will not be enough to solve the problem. You can have 25% that is enough to solve it, but they're not isomorphic because that doesn't solve the problem because you don't have all the information that's coherent. Now, if you get 95.4%, which is your target, why? Because 95.4 of the coherence is this. So 95% you round up, you get the problem solved. That's 100%. 0.4 down, 95%, you can still solve the problem 95% of the time. You're going to understand this, Namdi. So the PRP framework, phenomenological principle, on github.com/openexis is based on property set model on informatics, biological informatics, to scale systems to coherence. Now, how this works in practice: A to B, A then B, A then B, and then B O, B to A. So basically, you got this model too. This is called context switching model. So basically, you have to okay. this is introduction. So we're gonna come up to that Cartesian problem, Namdi. But let's go to the main thing today. Um, so we have to try to define this Cartesian to polar system properly. But this is how it's gonna work as a model without any inputs, which is just as a variadic system, which is called a model in the Biologicl philosophy. Because there's variadic, it can accept any input, but doesn't solve, it can solve a social problem depending on how you frame your problem. So basically, the context switching is defined like this. A context is like can be interpreted like I can say to you, I'm gonna go to I work daily on Obinex's website, which is gonna be out of the loop. It's gonna be basically no human's gonna actually be maintaining it because it's gonna be based on schema. It's gonna resolve itself. It's gonna fix itself. But the basically I say daily I take a shower. Does that mean every 2 days? Once every 2 days? Yes. And does that mean once 2 days every one? So basically, bi-direction just means like I can shower every 2 other day. Once I shower directly because there's no information to ground the meaning into the subject and it can be interpreted in 2 ways. So basically, it's a binary interpretation. So basically, did you shower today, Namdi? Yes, I shower today. Daily, I shower. Basically, every 2 days. 1, 2. I shower. 1, 2. I shower. Or the other way. Do you shower? Yes. Daily. So does that mean I shower today? No. Yes. So basically, we no or yes, but it's like you're not sure because it's because it helps the interpreter to decide. Interpreter programming languages, etc., like Python, things that just run and doesn't need to compile because they interpret the state of the computer. The program is not artifacted. So basically, I can say to you, let me try 2 days, 1, 2, 3, 4, 5, 6, 7, and this is daily one, daily. This is 0, 1, 2. I shower here. 0, 1, 2. I shower here. This is 2, 2, 1, 2, 2, 1. And this is now daily type 1, and then this is like type 2, type A, and this is type 2. Daily type 2, 1, 2, 3, 4, 5, 6, 7. Do you show up daily? Daily. This is daily. Yes. Today 1, 2. No. This is 1 to 2. 1, 2. Yes. 1, 2. Yes. So this is daily. So the first one is the first interpreter. As you can see, the numbers 1 to 7 represent the week. 1, 2 on the basically it's 2 knots. 2 knots to 1 cross. 2 knots to 1 cross, and this is like 1 cross to 2 knots. Because knots and crosses like that. So we have to ensure these two implementations are coherent based on the 95.4 metric, and that's why the interpreter is important. For the second reason, because the programs here, the nodes can context switch, can switch degradation properties. So basically, if I was not if this was a computer and there were nodes on a full-throwing system, which I defined as a peer-to-peer model, the system can take the role of a node as a circle or an X based on the healing system. Like the nodes can represent programs, any artifact that is cohesive, that share a symbiotic contract. The nodes can be doing one task can be tested and doing one task 95% of the time, and then delegate 6% of the tasks to the other node. But that's not really the goal. This is just one program set. This is just the main program. Nodes and crosses and bi-direction, so the X can do it to the 0, but it works both ways because they solve each other's problem when they fail to do something. But the goal for them is to basically, if I test this 100%, this delegation principle will ensure that this program X is doing this task, this one using doing this task 95.4, and this one because the system is coherent, it knows how to solve the problem. And now how the access is built. So basically, the goal is to ensure that this kind of interpretation isn't just binary as well. It can be plugged into a hierarchical state machine, like based on open questions, like how we. So this is a binary version. But we can have a open question. What did you eat today? Salad, using dimensional game theory, my model on dimensional game theory to for any non-determinate finite automatization, such as delay, deny, defend. Where defend and defer, or delay, deny, defer, are two states, two algorithms an actor can take to do it based on witnessing first, observing the state, and resolving the interpretation problem for directed instruction systems. Directed, remember, so we're gonna move on now onto this. So this is like a system that can interpret on the fly at runtime without getting bogged down in the mechanics. If you see here now the X and O. So this X, A, B. A, B are programs, jobs, tasks to do. But X takes priority of A, the task, and then does B. It doesn't mean it doesn't do B. It does B all the once, but it's more it's delegated to handle A when A fails. When A fails, and then B O does B. It just basically they all represent 95.4 times A and B, B and A by direction. But A is responsible for handling the fault of B. A is by root program X dot A and X dot B, and when X dot A fails, and it's needed by O dot A, because O dash context, the program X can delegate or can recover the actor from A and copy it, push it back to A. And that's called the healing. That's the healing in OBNX's philosophy. Because the program doesn't break; it just recovers the state it just goes back. It just tries to roll back the change of the system because it's decoupled. It's just seamlessly decoupled. There's no do it. It's based on Rust symbol of X and monoglot, a polyglot, and a hybrid system, which are for the OBI Heart or Soul UI UX library. Basically, this is another problem here. Namdi, go tell them what this is. So you see this model, Namdi? So tell them how you see it. So basically, in the UK, we got a specification. This UK light switch, the 1110 on UK. This basically, if I flip a light switch up, on the UK that's an on, and the US is an off. So we have to have like a master switch in the real world to solve this problem, because like something that's universal to use, like a switch that says like a master switch that can solve this problem. But that's not a problem. This applies to this problem too, because my pen just ran out of ink, which is kind of funny. Well, this is just basically I can try to formalize it now. I can try to formalize it. So basically, got a functor, define a functor that's he. A function that's heterogeneous. Heterogeneous functions are not uniform data, so they are not. They are. Let me try to formalize this. My pen just came back to life. I don't know why. So the UK has a 1 or 0, and the US has a 0 1. 0 1. These are two different systems for just switching a light bulb. So I can define the functor problem set whole whole as 0 0 and 1 1. This is uniform data stream, and this is a functor functor he, which is like the one here 0 1. So this functor are the mappings of the inputs. Always remember that, because you have to be in this problem set of frame as well. So if I want to switch it, I can define a canonical functor between H2 that maps the inputs bi-directionally. So when someone comes into a room and don't know this infer from the context of that room that this light switch I just flick up this way. With that overhead, like another switch or sub switch at the side, something that can be at the side. So let me try to find that out. So basically, the inputs are 0 0 are called uniform because they are the same type in that X plate, they are at the same time. But the one that I'm talking about on the road is heterogeneous, like the one that's there in the light switch standard. So basically, 1 0 matrix, 1, 0 on the X, and then 0, 1 on the Y. Or like X1, X0 or Y0 and Y1 is X1. Those are different systems. I'm saying to you, you can decouple this and decide how to so I'm trying to define it now. So how to define a switch, a switch. So basically the thing must interpret context. So basically if it's kind of I have to define the full context. So if I was in UK and the switch is off. This is what this is what I'm saying. The coherence operations really matters. The unit sets. Basically, I'm in the UK. In the UK, represent what? Being iota state. So the iota state will be like the default state being in the UK for the switch. So that will be to turn it on. I flip it up. I flip it down. So to turn it on, it will be one up, up. So I can say to turn on, toggle on, flip up. That up is an input, 1 to flip up, but that input is the chemical state. What is up? What is down? Because the enum says up down, and up down can switch. So that's what it is. And then for the flip up, UK, and that's called iota. Iota just means default state. If you think of Golang iota, that's just default state. It's not a preset state, it's just a default state for that standard specification, and that's what I'm talking about here. So I can flip up the switch. Now, if I want to flip down the switch, that would be what? No, that would be off. So on, flip up, and then down, shut down in UK, and then now that up and down is that is now is not up and down. It's basically relative. So I have to define there's another functor, which is another function for F he UK, and then I'll do F he US. US is down up. So this one is the US one. Now I have to find some kind of transition function that will take me based on the context already. Because I might not know what I'm in the US or UK, but my goal is to define an unknown state epsilon that can get this down without if it breaks I can debug it based on the encoding state of a direction instruction random access memory system. So the thing about this is basically down is up, up is down. I can say that the down off the down off in the US iota off is iota to iota on off US or down is off down up down up is the same as up down. This is now one set I have to consider. Now, see, basically that thing you've done up down up. This is called a matrix. So basically it's two vectors, but it's a matrix. And this is what this represents. This is a matrix here. Functor matrix, the functor up down. So this is computation I gotta use. So I have to find some kind of relationship between the context here. So this is like off only states. So basically, if I'm in the UK, if I'm in the US, down. If I'm in the UK, I put off. But this is if it's on, I put off. You can basically also design a nil state, which is nothing. There's no input, no output. But we can try to do it as nil down up, because that's more accurate. And then nil up down. So that's like nil. Nil just means like no memory. It's not null in C. It's void pointer. It just means nothing is being stored. No memory. No token type, no value is being processed, nothing is being allocated. The nil is like so the US nil is down to up. So it's you press up to turn it off. So this is UK one. So down is like up. So UK US. So this is like if this is nil. No. So this is nil or epsilon. So basically nil or epsilon is like down. Oh, sorry guys, I'm trying to do it properly. So the thing about this matrix, you gotta understand the matrix very well. So basically, you gotta like do it again. So nil Nil means nothing, and then nil up, nil on, nil off, and that is switch up, switch up, off, and this is UK. UK up is down, off down, and this is a UK function, and this is a UK iota for off. So UK iota for off, off, nothing, off, off, and then nil off, and then you go like a nil, on, nil off. The off is like up. So this is like a iota. The other state is very important. So you gotta try to represent. It's not a preset state. You do like a default state for the two specification, and that's what they have it. So for this to work now, there has to be some kind of operator here that's like a based on set theory. Because this is based on normal theory. It's based on you have to categorize it in a set. That's the transition. This has to be a set. Like, is this a set of offs? Is this a set of this is a set of offs? And this set is a bit off states. It's like the off states are like the nil states. So you have to have a functor that does nil to null and null to nil, and map that state to the on state, which is another functor based on specification. Because if I now say on is now on state is up in UK and down in US, that is correct. But the function doesn't know it. The context is nowhere. We don't know the context. We never assume the context. It's based on interpreted. So we have to interpret the situation and try to solve the problem. We don't even know where we are. In the States. Maybe we can be in any state. In the UK, and then we don't know. But we have to ensure that the system understands that we may not know this. So we can define a traditional system called a master state. But a master is just out of us. We just need to remove all the minimal stuff. So basically, we can now do this like we don't know, so we just turn off. We just reset to our IO system. So what the computer must understand to process, if I turn on, if I turn off and on in UK, turn on a bulb, turn on, I press up. So I prioritize 95.4 over time that based on probability, Bayesian inference, like that's Bayesian inference is like the probability graph of a structure based in K-NN clustering. That this is designed for this, so I'm gonna press up. I'm gonna push up, push down so the light will come up, and that'll be on. So if I push down, I get up, push up, and that'll be like the way it works in the UK and the US. So basically, I delegate I solve 95% of my problem, and then the other program in the same UK will solve the other 95% for the US standard. But it's a dual standard model. Based on the specification that's involved, and the coherence will represent like the enum states that are iota, and the iota is just isomorphic layer that's a union set, disjoint set, based on the system state, and that's what is called by context. Now, the context is coherence because you can track the context over time, and the context does not change. It's only interpreted. You can ask open-ended questions too. If it's not a binary system like this, binary interpreter, it defines a binary. You can have like a open-ended question, like open interpreter, like it's like what if I do? What is the based on like the category? Now the category can be verb noun or pairs. Now, why verb noun? What is a verb noun pair in other systems? So basically, a verb is like a doing word, an action, and a noun is a thing that's been acted on, the actor model. So this is very important. So you got a verb noun DAG, which is a concept model. So the verb is like fast car, slow car, stupid. Let me call that's just a car example. So this is example. So I can have a speeding car, a car that is fast, and that car is moving fast. But that car is moving fast one direction. It doesn't tell you. It's just a moving fast car, and the fast car is moving very fast to one direction. And then you can have a slow car moving slow in one direction. It doesn't tell you direction. It just gives you the faster the verb and the noun. That's what you're trying to resolve. Like the humans involved, have to understand the verb noun concept to ensure that the system is coherent. If you try to model a function like an error with a verb noun system based on classifying names, like the classifying names are really important to understand too, because if you have a warning, exception, error, and I'll come back to that now. So the fast car, slow car, walking dog, running dog, Running dog. The running dog is the action running, and the verb in is to do something, to act, to do, to run, running, to smoke, smoking, to to see, seeing, to observe, observing, to consume, to use, all of that, to consume, to act, that's what I'm using. The idea is to have two ways and resolve them with a category, a class, which is like the diag between the two systems. I can have a fast car, but I can have a fast car, but it can't be a fast car if I don't have a reference of fast. So this can be a fast car here, here, it can be a fast. This is like a one UK fast. This can be a US fast car here because the car is fast. Again, basically, it's crossing the dog. So basically, I can have a slow car that I can think is a fast car. So basically, if 30 miles is a slow car in the UK, then people UK and I think it's a fast car in the UK. Again, and I can think that I can really assume that the slow car is the fast car because that's the fast car in the US. And I say your car is the fastest car I've ever seen, but the same comes to far because that's a US car. Now the US car is faster, but it's not really faster depending on the 60 limit road map. So I can say standard road is 30 minutes, 60, which is true in New York. So 59 miles per hour is what it's saying, but that's 60 because that's the one you don't know what to cross the speed barrier in the US. You can drive 30 miles in the UK, but that's not fast. In the car, it's not fast. The car is just standardized to run that way because of the roads and the system around the ergonomic tree of the ecosystem, UK and America. 31 minutes 42. What else have I got here? Let me go back here. Yes, okay. So yes, so basically, my open philosophy, directed symbiotic evolution. This is like the one I want to talk about in my next video. Let me just upload this one first. But we got to understand that how this plays into directed symbiotic evolution and computation. Two seeds model and how it propagates through error schemas. Bubbles up and so basically look at this number. If you want, you have to look at this properly. Take a screenshot of it here if you can see it. Just tell your videos to look at these videos. Upload to TikTok. You should be able to make sense of it yourself. But this is why you are watching. You're trying to implement the directed instruction sets, symbiotic evolution sets. This is so basically, guys, this is the introduction. The next video will be the introduction to the system of directed symbiosis and how they effective of biological genotype. Genotype means like the genes involved, the genetic structure and the evolution, and how they create new type of phenotypes, which may be desired or undesired phenotype, the features of biology, based on us healing the generation of the bind. Okay, thank you guys.